Hello, welcome to Introduction to DDS for Mathworks Simulink users. I'm Paul Schmitt. I'm an RTI Field Applications Engineer for the New England area. Today, we'll take you through the DDS communications backbone and show you how DDS works in a system, and we'll show you how Simulink is a natural fit for that. And as well, we'll introduce you to DDS, the standard itself, and publish, subscribe, Datacentricity aspects of it, as well as the accelerated development advantages of DDS. And then we'll wrap up with a summary. First, a word about RTI. RTI was founded out of the Stanford Robotics Lab. It had a proprietary technology called NDDS, which is a distributed communications framework. The Navy was back in 2005 was using DDS. It was using Corba in a system which had a centralized broker, and they had a room, the server room, get flooded. And as a result, the ship lost full communications. And had they not been in dock, they realized they could have lost the ship. As a result of that, they came to RTI and asked RTI to. They funded RTI basically to take the DDS standard, to make it a standard with the object management group. And that way they could purchase off-the-shelf software, which was a requirement. RTI has the largest experience and the largest number of customers, largest number of design wins, 70% of the market. And we have over 2,000 designs that we've done. And I like to say that RTI has embodied that experience in three aspects within DDS. And that is, we've extended the APIs based on customer demand. And we work, because we're a founding member of the OMG standard, we work to make those part of the standard. They are carefully documented until they become part of the standard. And so I like to call that plus DDS, to use C++ parlance. Then the second aspect is where we have a large number of tools which help accelerate your development. And so that is part of this, that's beyond the standard. The standard will never encompass that. And so that's like what I like to refer to as DDS++. And lastly, with all this experience, we have a design team that knows a thing or two because they've seen a thing or two, to steal the line, tagline. And so they are available to help our customers out in terms of looking over designs, doing training, consulting, whatever's needed to make our customers successful. We are headquartered in Silicon Valley, and we have offices in Spain and Singapore. So DDS and Simulink. So what I'll do is I'm going to show you basically how DDS works in a system, just to give you a feel, a generic system. So on the left here, we have sensors, or something that generates events. And this could be radar, LiDAR, sensors of any kind, temperature read, whatever it is. And there can be many thousands of them. And in our Kennedy Space Center, we have, there's over 100,000 sensors in that system. The control units, typically of one logical control unit. Sometimes there may be several, it depends on the system. But and then there on the right we have the actuators, which that could be anything from an airplane aileron to a missile launch system. And again, there could be multiples of those. And these are all tied together over a connects, what we call a connects DDS Data Bus. It's a logical connection over a physical media. And so what this is basically the abstraction layer from your application and this data bus resides in libraries in each of these devices. And so what it does is it basically takes care of the communications anonymously with a publish subscribe data pattern, so that basically sensors can say, hey, I've got this topic and I can publish like a track topic with these fields, and at this rate of speed at this reliable or unreliable quality of service. And that enables subscribers to subscribe to that topic, and they can specify what quality of service they want on the topic. And if DDS will take care of the matching, it'll discover the entities, like the controls and the sensors, will be automatically discovered over a discovery protocol. And then the topics will be matched up. And if they have the same quality of service, they will, in fact, be subscribed to from the publisher. So this takes all that work out of the application. Additionally, the interface in each of these applications, whether it's a sensor, whether it's a control unit, whether it's the actuator, is interfacing to that track topic. So basically, you write a data model for your system. So you decide what types of topics you need to communicate. The sensors would communicate a track topic. The control may generate a command topic. And so you basically design your data model, and then the components of that data model interface to those topics. They basically, the data model becomes the interface for each of these components. And the beauty of that is this system may evolve over time. It may have many more sensors or different types of sensors and actuators, but each of these actuators and each of these sensors will generate a certain set of topics that have been predefined. And you can extend those, but generally speaking, what you see happen in systems is that those, even though the system may evolve, the topics in the data model quickly solidifies. And to give an example of that, if you look at the parameters in a topic associated with the track topic that we're showing, which might be a missile or an airplane, something flying, you know, it has a location, velocity, obviously the sensors that recorded it, and then you might have pitch, roll, and yaw. And if you think about that model today, in today's, you know, things that fly today, that's also true of the Wright brothers airplane. So what you see is that the data model quickly solidifies, even if the system has very large number of grows and adds on additional sensors, actuators. So here's an example where the sensors publishing track topic reliably at 100 hertz. The control unit has subscribed to it reliably at 25 hertz. DDS under the covers basically finds these components that want to publish and subscribe and matches them up. It sees that the sensor is producing the samples at a rate that can meet the controller's demand. In fact, it's producing it better than that rate. So it can basically guarantee reliable service, which means every packet in sequence, and the control unit's only asking for 40 samples a second versus the sensor unit being able to produce far more than that. Additionally, because we're a modularized or really a service-oriented architecture, we can add components to the system, such as a threat board, and it can subscribe to the same topic. In adding this component, we didn't have to touch any of the software in the sensors, the control unit, or the actuators. It's just one more subscriber. In this case, not only is it receiving the same topic as the control unit and the same topic that the sensor is generating, but it's saying I only need it best effort at 2 times per second, because it's basically a monitor that people are looking at. It doesn't need to have such reliability. There'll be samples coming along later that will fill that in. So it puts less stress on the system. So the application for that monitor can put that request into the system, into DDS, and DDS, the writer and the sensor, will deliver that traffic as the monitor asks for it. And the advantage there is really a few advantages. One is the application code itself doesn't have to have, you don't have to write a lot of application code to receive 100 samples a second and basically have to sort through them to figure out which ones you want or throw away ones that you don't want. So that's done by the middleware on the writer side. It also saves bandwidth on the data bus, since you're not publishing extra data that's being thrown out, and it saves CPU power on the monitor in the sense it's not having to sift through all that unwanted traffic and throw it out. As well, we can actually dynamically pass in constraints to say, well, I'm actually only interested in flying, objects that are flying at me at below 5,000 feet on this bearing at this speed. So that could be a threat situation. So you might only be alarmed for topics that meet that criteria. And again, that can be put into the system from the application running on the monitor, or the person controlling that can say, well, I only want these parameters. And that can be programmatically and dynamically changed. So that content filter can be added and only those topics will arrive. And you can dynamically change that. You can decide that you want to make that 6,000 feet or maybe bearing a different bearing or whatever you want. So it basically has huge value in terms of saving application development time, because the middleware is doing that for you. And the fact that the middleware can do that, we call that datacentricity. And that is that the middleware is aware of the topics and can perform either filtering or translations for you for the given clients on the client's behalf. And that saves, again, a lot of application development time. And lastly, because this Connect's data bus is under the covers, DDS is taking care of all the data marshaling, the normalization of big Indian to little Indian, 32 to 64-bit. That's all being handled by the DDS libraries that, again, are running in each of these devices. And that under the covers, there are point-to-point connections. This is distributed, but the connections for the data are point-to-point. That means that you have no intermediate hop, and you have no delays, no choke points, and that allows real-time, high-performance communications. So again, another advantage with DDS. And then the last advantage here, we're showing how we can add a version 2 of the actuator, and it may have a different topic. It may generate a feedback topic of some sort, status topic. And here, because we're modularized and because we're a pub sub, we don't have to touch the original sensor. We don't have to touch the actual code, or the original code in the original actuator. Only the components that want to take advantage of these new topics need change. And in fact, there are even ways, depending on how, when you're evolving a topic, which does happen, where we can do that in a very graceful way to allow new topics, new devices to talk new topics, but yet still handle the older topics, as well as old devices handle the base of a new topic. So if a new topic's built from an old topic, it can actually build upon that and still do the old functionality on the old part of the topic. So there's a lot of mechanisms to allow DDS to gracefully transition from one level of system to another, and that's another hallmark of DDS. Lastly, we have a secure add-on, which I'll talk about a little bit later, but what it does allows us to do authentication and encryption on a per topic basis. And one thing to note here, when we're talking about the not only can we do things on a per topic basis, we typically can do things on a per topic per endpoint basis is a common thread with DDS. So the fine grain quality of control, fine grain security, basically everything with DDS is centered around topic and topic endpoints. So here's DDS working in showing it working with Simulink and the advantage and why you'd want to use DDS with Simulink. So on the left engine is a real, obviously, jet engine, and RTI is in avionics and in aviation, and we have customers using us in engine components. And the key there is that that's very expensive, and to be trying software out on an engine, which could be very, if you miscontrol it, you could destroy the engine. It's millions of dollars. So the ability, and actually a danger as well. So the ability to run a simulation of that algorithm and to test things in a digital twin has a huge advantage. I can obviously do a lot of testing without expense and without danger. And so using Simulink in that environment to model those algorithms and to model the system is really important. And the ability to integrate DDS as Blockset does with Simulink, and the ability to have graphical interfaces to allow users to easily do this is a huge advantage, because now I have a digital twin which is very close, especially from the application point of view, to the actual software that's going to run the system. I don't have to pull software out or compile it with different flags of whether I'm running in a simulator or not in a simulator. This application doesn't know that it's running in a simulator. And the beauty of that is there's less chance of a mistake, more accuracy in our simulation and modeling, and less expense and less danger. So that's the advantage of a full model-based design and simulation. And it even generates code. DDS, the box set will even generate DDS code. And here's some of the advantages of Blockset by Mathworks. That is, you get the full modeling, you get the dictionary, DDS dictionary, lets you manage and create, edit your DDS definitions, Simulink. You get Blockset provides publishing, subscribe, samples DDS, and quality of service. it generates also C++ code and XML files, and XML files are very important to DDS because they often let you control the quality of service without having to. You can do it programmatically, but you can also do it through XML. And the huge advantage there is you can basically tweak and tune your quality of service without having to recompile your whole system. You can actually do it on the fly, so it makes it very fast development cycles. And it fully integrates with RTI Connect's DDS. So what we look for, whether or not customers need DDS are the following. We look for 3 of the following items, generally speaking. This is just a guide to give us an idea. Should we apply DDS here? Is DDS the best fit? Because one thing we don't want to do is get into a situation where we've sold somebody DDS and they really realize they don't have that much complexity. But sometimes things evolve and can become complex too. So, but anyways, here's, key thing with DDS is, do you have severe consequences? Your system goes down for 5 milliseconds, for 5 minutes. And, DDS is battle tested, literally battle tested. And we have a lot of customers using a lot of building blocks for redundancy in the controllers. So you can basically have redundancy in hot standby, taking over for active failed. And that gives that basically helps tremendously with the reliability and redundancy. Also the real-time aspect, milliseconds or microseconds, and DDS is point to point under the covers. It takes care of that for the application, and because it's point to point, no bottlenecks, no choke points, and no relay points. We do get really good performance, and that's key. The interface, the ability to scale to large applications, and I'll show you a couple of ways we scale within what I call horizontal and vertical scaling, which allows you to have many thousands of applications running in a DDS system. Data flow complexity. Does your data have many destinations? Especially, do you need to treat that data differently to those different destinations? And do you need to treat data differently amongst itself? And that's to get some of the advantages that DDS offers. And so that's key. Having military grade security, part of the DDS standard, and what RT offers is a add-on military grade, basically public key encryption, as well as AES public key infrastructure, as well as AES encryption. So it allows authentication and encryption in a military grade. We have many military customers using DDS Secure. And the advantage of DDS Secure is you typically can develop your application without Secure and add on Secure without writing a line of code. You basically put the artifacts around on your system that are signed, governance files and permissions files, and then that security is shared during the discovery process, and only those participants that are allowed to see certain topics and allowed to do certain things with topics can do those things. And so that is a huge advantage. Then the only time you'd have to maybe change some code with security is because security does take on the order of 20 or so % overhead to do the encryption. You may be up against, if you've got a system that you've done tight design where you don't have a lot of headroom, you might have to retune your system and rewrite some of the code to allow for that. But most of our customers can turn security on and off, and it makes for very nice incremental development. Architecture. DDS typically isn't something you're going to shoehorn in after the fact. Although, having said that, if you do have a publish-subscribe paradigm of some kind, we have had customers do that, and so it is possible. But generally speaking, you're looking for somebody who's looking for, is doing a new design, and they basically, looking to use DDS, and that's the time to get it into your system. So those are the aspects or the characteristics of a customer using DDS. DDS is an OMG standard, so it is part of the object management group. RTI is one of the founding people that basically put the standard in place. And so the standard is really more than just one standard. It's not only the data distribution service, but it's also a number of other standards that define the real-time publish-subscribe protocol, describes the XML syntax, security, interface definition language, number of things. There's 10 specs shown there. So it's a fairly involved standard, but it's used in not only as DDS as its own standard, but it's also a standard used in other standards, and I'll talk to that in a bit too. So again, just to kind of summarize the object management group data distribution service, it has you have the middleware sandwiched in between the northbound APIs, which allow for cross-vendor portability, so that there's no vendor lock-in, and this keeps, of course, RTI competitive. We have to keep ahead of our competition to make sure people use us. And then on the bottom of the stack, there's the real-time publish-subscribe protocol, which allows us to interoperate with other vendors. Or if you as a customer are using DDS and you're integrating with some other device, because it's a multi-company development effort, which often the case in these large systems, the other company may select a different DDS implementation, and it's important that they, as long as they're talking the same model, they can talk we're using the same protocol. The DDS is part of the standard. It allows this cross-vendor interoperability. And lastly, there's this DDS Secure plugin, which I spoke to earlier. So that these APIs are key to the design. The highlights of DDS is that it's data-centric, and I'll talk more to that, but we've talked a little bit already. It's modular and distributed, publish-subscribe design pattern. And that is really great for not only fault tolerance and security, because you're compartmentalized. There's no single point of failure. There's no blocking or relay point. But it also creates a massively scalable system because there isn't some centralized server that can top out. Every device that plugs on the bus usually brings a processor with it, so it's much more scalable. And there's some other scalability techniques we have in addition. It's real-time performance, as we've mentioned a few times, because of the point-to-point connectivity, ease of integration. That modular design and system architecture design really allows for you to develop to a data model and then have different groups go off and work on different parts. And then the other advantage is they can actually, and we've actually done this, where we've taken our recording service and recorded what we've generated, had one group record what it's generating and email that to another group and feed that in as their input to do unit testing. So a real advantage there in terms of ease of integration. Automatic discovery. I talked about this briefly. I have a slide later on it, but the fact that these participants on that DDS data bus find each other automatically is very key to DDS. And transport independence. Out of the box, RTI's connects DDS, connects over UDP Ethernet and as well as IP, and it also connects through shared memory if you're on the same processor to save even higher speed. But the standard itself has a designed interface API for the transport. So we've had customers put their own transports in, and we have an implementation of a serial transport as well. Rich set of fine-grained quality of service options. There's over 20 QoS options available. And again, it lets you tune things for individual flows, whether you want reliability, whether you want deadlines, contracts basically between the application and DDS, and alert if you don't meet those contracts, if the application misses that contract, whether data becomes stale after so much time, whether entities go away and are considered basically a health check on entities. So there's a lot of capability in the quality of service to allow what people need, applications need for communication. Again, I mentioned this briefly, but this is showing DDS as a standard within standards. Every one of these standards calls out DDS as a means of communications. Some actually even call out RTI DDS. So we have a couple, ROS, very popular in automobiles as well as in robotics in general and medical. AutoSAR, of course, automobiles. FACE is a future airborne capability environment, which from the Air Force that calls out DDS. UMA is the unmanned maritime autonomous architecture by the Navy. So there's a lot of serious standards that call out DDS as their communications infrastructure. So let's compare DDS to other architectures. So typically, when one starts out designing or before DDS, you would use sockets and you'd connect those up, and you probably, generally speaking, you'd pretty much hard code who's talking to who. And the system, as it expands, is somewhat brittle because you have to tell the receivers, you have to go in and muck with the receivers code to make sure they know who this device is talking. The new device you're adding, of course, that's new software anyways, but you often have to touch a lot of software through your system. And this can become quite complex, really an n squared problem over time. And it's awfully fragile and brittle in terms of writing new code. And so what happens, and I've been in this situation with products I've developed in the past where you're really focusing on an application, but it's a rather complex application. You have to communicate amongst a number of devices. And so you have to put in some kind of infrastructure to do that communications. And you spend a lot of time adding these capabilities in, or some subset of these capabilities. So these are, and you may not spend as much time as you should on these. So you're not going to be extensible as you have new requirements. Those requirements maybe go unmet, or they get put in haphazardly after the fact. So this is the problem we're solving: is allow customers to focus on application logic and take care of the communication stack. It's what we do. It's all that we do, and so we can do it well. So here's a different approach. It was first, and this is what got the Navy in trouble, that example I showed, where they had a centralized broker. And we've talked a little bit about the pitfalls of a centralized broker. But the nice thing about a centralized broker is you do have a publish-subscribe. It is a software-oriented architecture where you can add modular. It's modular. And in fact, in the core implementation, they even have a interface definition language, which is used by DDS as well to define the topics. It's data-centric, so it has a lot of advantages of DDS. And the only disadvantage it has, so let me just, just go to the diagram here. So it's actually helped out a lot in terms of taking care of a lot of the problems that the previous sockets-based design. However, as we've intimated, it basically introduces some issues. It introduces a relay point, which is latency, introduces throughput bottleneck potentially, scalability, because as you add more and more components, they have to communicate through that centralized server, and uptime. That centralized server goes down, the system goes down. Or you have to build some kind of redundancy into the system to keep the whole system up, as opposed to, which, even with DDS, you may need to keep critical parts of the system up and build redundancy in. But the point is that any given system can go down, it doesn't affect the other systems. So anyways, this is, with this approach, it has some pitfalls. What DDS does is takes this approach and really federates that broker out into libraries that run on each of the applications. And so that's what this diagram, the darker blue are the libraries that are running that are really implementing that broker approach. So there's no broker in DDS, but there is the broker functionality, but it's being implemented in each of the components. So there's no single point of failure, there's no relay point, and there's no choke point. So it's just much more efficiency. Additionally, DDS calls out the idea of having logical domains, which are namespaces, and those can be either over different physical media or the same physical media. And so if you're doing hundreds of topics, you may find that those topics group in natural ways, and there's no reason for you to be communicating one group of those topics to the other group, except maybe rare cases. And it's just more efficient and even higher performance to separate these logically out onto domains. And from a security point of view, you get compartmentalization. And we offer an out-of-the-box, again, this is one of the features of Connect's DDS, we offer an out-of-the-box routing service, which comes with your bundle. We offer a number of services. I'll take you through those, and they're beyond the standard. So these are just things we offer. You can turn them up in your application, and now you can route between these two domains and take some subset of the topics that need to flow between the domains. So primarily you might have domain 0, which handles one group of functionality. Domain one handles a separate group of functionality. In some cases, some topics may need to flow between them. You can do that with a routing service as example. So really what RTI does and what Connects DDS does is takes all that stuff that you have to do and does that, in the DDS, Connects DDS middleware. It lets the customer focus on the application. So here's an example of the previous message-oriented, message-centric design, and now moving to a data-centric design. And there's obviously the savings with the addition of benefits of auto discovery and not worrying about system startup ordering that DDS provides. And here's an example of a customer that they had a legacy system, didn't particularly have a very good reputation. They had 500,000 lines of code. It took 8 years to develop, 21 servers, tracked 20,000 objects. They rewrote that code using Connects DDS. They did a proof of concept up in about 2 weeks to show that they could do what they wanted to do. And what they really realized was most of that 500,000 lines of code wasn't doing the application. Only about 50,000 lines of it was. The rest of it was doing all that data marshaling, all that coordination between entities. And that really is what DDS does and does well. So they were able to get this up and running 1 year, running on one laptop, achieving over 10 times the performance. This is a quote from the officer in charge of this program, and I think it speaks for itself. So talk a little more about the discovery process. Basically, the first stage is participant discovery. So the participants advertise themselves, and they actually continue to do that every 30 seconds. Typically, you can tune that to whatever you like, but default, that's what happens. So basically, these participants can learn about each other, and each of them keep that database of what's on the data bus in their own libraries or in their own system. And so again, that's that distributed functionality. And so as they learn about who they are and how they like that's typically done over a multicast channel, the initial discovery. But once they respond, they basically say, well, talk to me actually on this channel. And so they can give a different interface. And then the communication then runs over that interface. So it's very flexible. The second stage is saying, okay, I've got a participant, but is that participant interesting? Like, if A sees B, is B an interesting participant? Is B going to subscribe to a top DDS? The application A doesn't really have to care whether application B is going to consume its topic, but DDS will do that pairing for the applications. So the application only has to know I've got people out there interested in my topic. You can actually, from DDS or APIs, to learn who's subscribing to you or who when you're matching up, but that's optional. The DDS is doing it for you. So basically, the writers and readers will be matched up depending on whether they've got compatible topics and depending on whether they have compatible quality of service parameters. If A is producing unreliably topic and B is looking for it reliable, that's not going to match up because B is requesting that no packet ever get missed, and A is not guaranteeing that. So DDS will do that matching up, and we have some really great tools to let you look on this bus and analyze this bus, and as well as see why. I've got A and B. They're looking at the same topic. Why isn't B getting what A is producing? And you can look and say, oh, I see the quality of service isn't matching, or the rate's not matching. So some aspect of it, the tool will show you what's going on, give you visibility into your design. Again, these tools are beyond, they're not part of the standard. They're RTI Connects DDS tools. And it's just showing the completion of the discovery process. So just to show you how DDS stacks up against other other semi-equivalent functionality, we talked about the TCP sockets over on the left and how brittle that design is. Moving to these standards, they're all broker-based, and we've talked about the problems of broker-based designs. They start to help, but they introduce the problems of choke points and of redundancy issues or failure, single point of failure issues, and performance issues. So, and moving to the publish subscribe, the problem with these guys is that they typically aren't data aware. They're typically, the data is opaque. In fact, all of these, that's the case. The data is opaque. You can't put requests into the middleware to say, hey, I'm only interested in this topic, but only with these constraints. Basically you get all of the stuff delivered and then you sort it out in your application. And that leads to less efficiency and more application development. And then this is another broker-based, this queuing type mechanism, and it's broker-based. So again, centralized. And many of these are not standards. So, you're at will what changes from version to version, as opposed to DDS, which is standards-based. It is data-centric. It is real-time, non-brokered, and that's all key. Those are the unique things that separates DDS from these other technologies. And just to give you an example of this and how ubiquitous DDS can be, out of the box, so you can run DDS on any of these layers, and it runs in real time because there's point-to-point connectivity. Between these layers, obviously you're going off through some kind of wireless connection or a WAN or through the internet. You'd use RTI's routing service, and maybe you'd use our WAN connectivity service. And so these allow you to transport some or all of the topics out of the vehicle up the stack, typically telemetry. And typically it's less real time because you can't guarantee, depending on the link that you've selected, you may or may not be able to guarantee the real time performance. But what this lets you do is it lets you have DDS on every layer and it lets you have DDS between every layer. So you basically have ubiquitous DDS capability, which is really nice because now I can move functionality from one layer to the other. In fact, we have customers doing this with the UMA, the underwater designs, where they basically are initially tethered, and somebody's doing teleop to the vehicle. And as that vehicle submerges and disconnects from the wireless, it loses communications and goes fully autonomous. The control functionality is obviously disabled at the teleop station and enabled on the device. So you basically can have functionality shifting, if you will, between layers. Additionally, RTI Connects DDS offers services in the cloud. And we're cloud agnostic. We don't care which cloud you use, but you can put into the cloud a web server, a DDS web server called a web integration service. It will put one foot into the DDS and bus and register and subscribe with quality of service parameters, just as any application. And on the browser side, it will provide either a RESTful interface or a WebSocket interface to your application, which is JavaScript. So it's very flexible. So just to summarize, the DDS Data Bus, distributed, resilient, no single point of failure, massively scalable, modular, compartmentalized, real-time performance, plug and play flexibility, standards-based. Just re-emphasizing the performance. And let's talk a little bit more about the data-centric publish-subscribe model. So data-centricity, just really talk about data-centricity here. We like to think of data centricity as data in motion versus data at rest. Database is data at rest. It's data that's happened in the past, and you're now putting queries in to do analysis on that data, and maybe using machine learning or whatever to take out latent information out of that database. With DDS, you're actually registering for data in motion, data that's going to happen. So here is a content filter, very SQL query-like, where the content filter is saying, hey, I want this topic, but I want it to match color red. I want it to be greater than 10 in the size. And it could be any parameters depending on what your topic has for fields. But the point is you're putting in a request for what will happen in the future. And we do have a service, a database service, excuse me, which lets you store that data into a SQL database. So you can do post-processing as well. But the point here is that DDS can actually, if you will, put in queries for data that's going to happen. And so it gives you a tremendously powerful capability, and again, saves the application from getting a lot of data it doesn't need, doesn't want, and then has to work through to get rid of. So it's a real advantage. And just to drive home this data-centric model a little more and just kind of show some of the terms, you have a domain, which is basically a namespace within so basically things in a domain only see each other and they're isolated from other domains. This has a lot of advantages in terms of isolation and modularity. Then you have a topic, which is basically a table. And in that table, you can have topics of different keys, like a database. So here we have either the flight number with the airline, or in case of sensor ID, those would be unique keys to identify a row. But the structure of the table is defined as a type. So you'd have a Southwest airline type, and you'd have a United airline type. And so that basically, that type, but they're both of type airline. So you have a type for each instance. And so we call that, and each instance is keyed by some unique identifier combination of, to have a unique identifier. And again, each instance is basically a row within a table of a, that's described as a type. And then in each row, we have samples. So in case of any of the airlines here, we're showing a sensor. When you get updates to that instance or updates to that row, you basically get, those are samples being delivered. And that's actually what gets delivered over the data bus, is a sample keyed to a particular type and or instance rather, and then it's structured as a type. So that gives you a lot of flexibility in terms of being a database like analogy. In fact, that's why we call it a data-centric model. Again, another hallmark of DDS is helping customers migrate. And we have two things that let you do that. One is it's one mechanism called X types. It's not as one of the standards. And what it lets you do is basically define within. So here we're showing a customer creating a topic and creating really a data blob. And so they've got a loosely typed system. It's not strongly typed as you'd want for a DDS. If you're starting fresh, you just strongly type it so you can have access to every field. Kind of the advantage here is that the sensor, this is self-documenting. I can look at each of these fields. I know exactly what they are. They say what they are with tags. The tags are often way bigger than the actual data it's carrying. But I can't really get access to this until I get it into the application and sort it in the application. So the advantage of DDS is that I can actually let DDS do that sorting. Also, an advantage of DDS is we kind of combine the best of both worlds. During discovery, we communicate the type or the structure of the topic. And that allows us to send the topic itself operationally in binary form. So you don't get all this overhead, but yet you can still read the topic because you know what the structure of it was when you receive it. And our admin console tool lets you do that very nicely. It monitors the bus, picks up the type structure, sees the matching data, and it can dynamically show you the data moving across that bus, which is really nice. So in this case, the customer what they did was they wanted to use DDS in other parts of their system and eventually use it on this system. So they basically put it into a blob, got their system up and running. So they got the advantage of interoperating with DDS, but not really the advantage of Datacentricity. What they did over time was they teased out the fields they wanted into a IDL type structure and put a key, keyed on the ID, and then they kept the rest of the data in a blob form. So basically, they can get access to these aspects of the data and filter on that: the sensor ID, plant ID, and the version. And then over time, you can migrate to a full strongly typed system. So again, nice way to migrate to the system. Another way that DDS provides extensibility or way to transition your application from one version to the next is by having extensible type definition when you're defining your types. So in some cases, if you're implementing a standard, you never want this type to be able to change. It's part of a standard. You don't want anyone changing it because you want to make sure you adhere to the standard. So here it's called a final type. So you just wouldn't change it. Next is there's actually a tag you put on the end here, which says whether it's extensible or not. And in this case, we're saying, hey, we're going to take the same topic and we're going to add on and allow it to extend to be an elevation topic. In fact, if this is structured such a way that this air track topic actually inherits from a track topic, you can go both forward in time to a newer service, which can see both the base and the new topic and deal with both of those perfectly. or they obviously can't do elevation on the track topic, but they can treat the track topic as much as possible like the air track topic. So they have the ability to read both types and discern and show both of those. And the alternate also goes if you have a new device generating air track topics and it's got a base of a track topic, you can actually, when it talks to an older entity, that older entity will only get the track part. So that allows a newer uh, participant to talk to an older participant and get the old functionality. You won't get the new functionality, obviously, but it just makes it much easier in terms of evolving your system. You don't have to do that forklift upgrade that you're typically used to doing, where you have to convert the database, and if you want to fall back to the old system, you got to reconvert the database, pad out fields, do all kinds of stuff that you probably haven't tested very well, and then you have, because you don't do upgrades and downgrades very often. So DDS takes care of this, makes it much easier in terms of your system. And we even offer a mutable type. This is all part of the standard. This does incur a little more overhead during operationally. You're communicating the actual topics, but you can actually move fields around and tie them together with the key as a common field. And this just shows you some of the different quality of service, traffic is an automobile case here, where you have different things like cameras, LiDAR, radar, GPS, command and control. And these all have different attributes, data volume and frequency, and even reliability. Typically cameras, you're not going to retransmit. You're getting enough data fast enough that once if a frame got corrupted, you ignore it and you move on. Where that may not be, obviously not the case with command and control. You want to make sure that that gets delivered reliably. So DDS has QoS capability to let you do all of that. So here's, I talked about over 20 different parameters, and these are kind of the industry standard terms that you're used to seeing, rates and filtering and fault tolerance and latency management, et cetera. DDS has slightly different terms for these, but I think they actually are more meaningful in a lot of ways. But they basically allow you to have reliability, to know whether your application's gone south because it hasn't reported in by liveliness, whether the data hasn't met its contract and the deadline, who owns the data, flow control mechanisms, different efficiency mechanisms like batching, asynchronous publishers. So they have a lot of different QoS aspects that allow you to manage your data between different endpoints. And again, this can be configured with XML, or it can be done programmatically. And it's independent of the underlying transport. The real-time publish-subscribe protocol is below this layer and is part of the standard and takes care of, basically handles this transparently. So this shows you what Connect's offers. I talked about Connect's being beyond the standard. I talked about it in a couple different ways. One is where we've extended the APIs and documented those. The other way that we, and this is based on customer experience, based on thousands of designs that we've done with customers to know what they need and what they're looking for, and years of work. So we have I'll just take you through these very quickly. We have we have the a code generator. So basically this allows you to take your IDL, your data model, and it generates some reference code for you, publisher and subscriber, so you can kind of have a template to get going and work with. A routing service, I talked about that in a couple of different cases where we have a router. We can route topics between domains or even from one domain up onto a WAN interface to connect up into the cloud or wherever you want to go. So that's an SDK, so it can actually you can plug in programmable transformations. So it has some built-in capability to transform things, but you can also do custom transformations. So it's very flexible. Data persistence, this is a great application for this, is where you have a redundant controller, you have commands, these controllers are issuing, those commands have to be based on integrating a number of samples over time to decide what the right command is. And so you have a backup controller starts to come online, it's got to wait for n samples before it can start issuing commands, even if it's online. So so after waiting n samples, it then can go hot standby. Where with data persistence, what you can do is you can say, hey, I want those n samples, I want your last 20 samples now. And it can instantly integrate and come online much faster. And the persistence service takes care of that even if the writer goes down and fails. And with persistence, it also does it if the whole, if the persistence service goes down and comes back up, it'll have, if the system goes down, it'll store that over a power fail. So that's again some of the building blocks for redundancy in systems that need redundant components. Data queuing is a service that basically, if you've got a producer of data, let's say it's producing flight times for all these different airlines, and you want to have different servers handle each airline, United server, American Airlines, Southwest, whatever. The data queuing can post that data based on a field. It can discriminate and post only the Southwest airline data to the Southwest airline server, et cetera. So it allows for parallel processing or for individual processing of the same data type, but some different parameter on the field that you want to index by. Record and replay is just unbelievably good in at least 4 different ways. You can use it for black box telemetry in your application. Again, this is part of the license, no incremental cost. So you can use that as an application to basically keep telemetry when your system goes out of communications. You can use it for development, unit testing, recording. As I talked to you about what we did with our development, we had different modules being developed to the same data model. They had different functionality to create the system. And one group was able to record what was going on in one application and hand it to another group through email and able to record and replay that into the system to see how we'd respond. And when we came to put the whole system together, the integration was much smoother because we'd in effect already done integration. And then you can use this in system test, record and replay. You can do translations, and you can speed up. So for system test, you can do stress testing as well as replace hardware with pre-recorded entities that are running in your system, and they look like they may be running in a loop, and they put extra stress on the system or mimic hardware that you have to otherwise buy. So you can use record and replay to simulate, and you can use it for post-action analysis, as well as we've had customers even use it in their trainers to introduce different scenarios. So it has a lot of use. These next set of tools are more for tuning and debug. System administrator, you plug it onto a bus. It does require a GUI, typically is run on a laptop, but you plug it onto your system. Typically people have an Ethernet backbone of some kind, but anything IP, you can plug it on, and it'll basically monitor all the what's going on that data bus, what routing, what services are running on those data bus, what topics are running across that data bus. You can look at the data, you can visualize the data, it'll graph the data for you. So it's a great tool to basically start debugging your system with and figuring out, and even doing analysis of what's going on in your system. Even if you think it's running right, you can take a look at what's going on. System inspection. We have a couple tools that do they allow you to publish known topics to verify that if you're not connecting across the network, as well as they can dump out information that's going on your network. These are particularly good for embedded environments because most of that you can do with the system administration tool, but these are good for embedded environments where you can't run a GUI. They're command line based, so you can actually see topics get printed out to you on that embedded system, or you can ping, if you would. We have a thing called DDS ping, which lets you not only do it's more than ICMP ping. It's basically sending a topic and saying it received a topic on one publisher, one subscriber. So you know that you're not only communicating, but you're communicating with topics across that bus, which imply discovery and a lot of other things. System monitoring allows you to basically plug in some libraries that are instrumented into your system, and then you can see how, like, cache depths and bandwidth performance. Helps you tune your application if you need to do that. It gives you visibility into the internals. Database integration allows you to integrate and store data into a SQL database. Web integration service, I spoke to that earlier, lets you connect to a RESTful or a WebSocket interface on one side and DDS on the other. We have a spreadsheet for Windows users, lets you graphically see what's going on and even publish from the spreadsheet. And we have a lot of third-party integration tools. And of course, Mathworks is one of the key tools. In the larger blue box, we're showing the DDS Professional and Secure. And as well, we offer the Micro, which is for resource constrained systems, smaller version, subset of DDS, a little more statically configured to fit into that system. And then we have CERT, which is a variant of Micro, which is extremely locked down so that you know that all the resources are pre-allocated as required by the FAA certification process, and to make sure that every line of code's been validated. It's quite an expensive process, so minimizing the code for that reason as well ensures that the code is doing exactly what it's supposed to do. The process of getting through a cert is pretty intense. So just to give a summary, kind of all the tools, services, utilities. I think we talked to most of those. Different language bindings. We have C, C sharp, C++, a couple different varieties, even Ada and Java. So there's a lot of different, Python's a newer one coming out. So, and we have a lot of connector language bindings as well, like JavaScript, which are available on GitHub, which let you use a subset of DDS for scripting language. So those are pretty nice as well. And then, we showed the security, safety certification. So to summarize, DDS is an OMG standard and a base standard for other standards. It's distributed real-time, data-centric. No broker, no choke points, no single point of failure. Sufficient real-time point-to-point connectivity under the covers, and the data is the interface. So that allows for modular, as well as that interface becomes pretty stable pretty quickly, whereas your system may keep evolving and extending. DDS is a proven technology, particularly RTI's Connect's DDS. We have been in many mission critical, absolute mission critical systems, air combat control systems, Grand Coulee Dam, things have to be online 24/7, upgradable online. That's where DDS is very strong in systems like that. Flexible and extensible, we've talked about that. And of course, working with Simulink and Blockset is a great combination because these systems are large, they typically are expensive, they may even be dangerous. And so having the ability to simulate this, in a very accurate way and even have that graphical modeling is absolutely key to be able to make a great development environment for our customers and minimize cost and safety hazards as well. So great combination. And that's it for me. I appreciate your listening. Thank you so much.